So for this lab, we did the stereochemistry using 3D molecular structures. So I built two different ones. One that showcased what a non-superposable mirror image was, then one that wasn't a mirror image. Then I also focused by measuring the optical activity of elane, dextrose, and fructose using a simplified made polarimeter. So the phenomenon that was measured in this lab was the optical activity. This occurs because the triol molecules contain an sp3 hybridized carbon, and it's bonded to 4 different groups. So just an example here. So it's asymmetrical. It's kind of hard to tell from my drawing here. It makes the molecule non-superimposable on its mirror image. So when the plane polarized light passes through the solution, so let's say this is the solution, the light can be rotated either clockwise or counterclockwise depending on the configuration. So then, boom, light passes through, goes down, and this is where you can tell if it's either clockwise or counterclockwise depending on how the light rotates. So since it is asymmetrical, so let's say you find the extinction point and you go until you find it again, then you can go around the whole circle and continue to find it because it is asymmetrical. Why do various compounds alter the results? What causes the difference? So each compound has to have that asymmetrical center, but they're all going to be different on how it's set up and the arrangement of those atoms. So in my lab for the elane and dextrose, the rotated light was in a positive direction, while fructose rotated in the negative direction, so the counterclockwise. Then the positive was the clockwise. The differences are caused by that center, as I discussed, and how it interacts with the light. So they're not going to be the same because they're different compounds. How do you know these molecules are all optically active? So I know they're all optically active because I was able to get the rotated light. So that tells me there's at least one sp3 carbon atom that has 4 groups attached to it. How do the concentration, purity, and identity affect the results? So the calculation for the specific rotation used the observed angle, the path length, and then the concentration of the solutions, so the height in decimeters. If the concentration was impurities such as the concentration being measured inaccurately, anything that could have been in the solution that wasn't supposed to be there, hair, dust, let's say the solids of the solution accidentally got in there, that would also affect how the light is hitting the molecule. So none of mine matched the theoretical values that I was given. So there may have been some inaccuracies there because I had high % errors. So what must occur for the phenomenon to be observed? So kind of as I said before, it has to be trial, so it has to have that sp3 center It has to have at least the 4 connections, the 4 groups. The light has to be polarized. Under those conditions, then you should be able to detect and measure that angle. Then my results showed that alanine and dextrose, as mentioned before, had that positive rotation while fructose had that negative rotation. Even though my percent errors were large, the experiment just showed how stereochemistry and polarimetry are connected and how the structures affect the optical activity. So for each solution that I measured, they were all different. So that tells me that the structure of the solutions were built different.